Chapter 1. Introduction. This is a book on quantum mechanics. It starts with the pre-quantum physics history that leads into quantum theory. A thorough description of the modern Schrödinger and Heisenberg theories and applications is then given. Material used in this endeavor draws from lecture notes and material from over a dozen excellent quantum mechanics textbooks. For further detail on any given topic, simply explore the textbook cited in that section. After the standard undergraduate-level quantum mechanics description, a more mathematically formal construction is made with Dirac's axiomatic description, and more advanced quantum mechanical issues are addressed, such as relativistic quantum mechanics. At this point, we've reached the normal extent of a first-year undergraduate course on quantum mechanics. In this book, however, part of the selection on quantum mechanics topics, or emphasis, is meant to connect with Book 5 of the series on quantum field theory.
Thus, examples and background development relevant to establishing a quantum field theory motivate part of the selection of advanced topics. In the quantum theory described above, the quantization approach is equivalent to canonical quantization, and it will do a great job giving the spectral lines of hydrogen and other atoms, as will be discussed, but there are areas where canonical quantization, directly, is not an optimal approach to quantization and getting results. Instead, there is the Feynman path integral formulation of quantum mechanics, so this will be described in detail as well. The path integral approach is not optional in quantum field theory, so it is good to understand it in the first quantization context anyway, as will be seen.
So far, the book description covers undergraduate-level material and graduate-level material preparatory to a quantum field theory course. Part of the objectives of the series of 7 is to cover the fundamental physics topics and to tie them into the most modern physics understanding, with direct connections given in Book 7 to emanator theory. Thus, this book will also discuss quantum measurement theory, with objective reduction due to objective emanation described in Appendix D and Book 7, and the nature of time. In this book, an attempt is made to tackle the problem of time, and to see if a direct quantum gravity solution can be obtained in a highly symmetric, simple situation. The complete analysis of the quantization of a gravitational dust shell collapse, Chapter 7. The mathematics is for a fully general relativistic dust shell collapse, which is lengthy, so is partly placed in an appendix.
Then a choice of time reparameterization will be given using a new type of time reparameterization, and using this to full advantage, a quantization of the dust shell collapse is successfully completed in a fully self-adjoint formulation. In the process of doing the quantization, a greater understanding of the subtleties of time is obtained. Not surprisingly, the nature of time is too large an issue to be resolved in the context of the mini-superspace problem mentioned above alone. Instead, further developments in thermodynamics and black hole thermodynamics will be needed first, explored in Book 6 and Book 7. Thus, in this book, number 4 of the Maximum Information Emanation series, we begin the transition from a classical formulation of reality to a quantum formulation.
In the classical formulation, we often had system descriptions involving position and momentum that described a classical trajectory, e.g., a solution to a differential equation on real functions. We saw in Book 1 of the series the expression of the classical solution to the real differential equation could also be expressed as an integral expression involving the Lagrangian with a large real exponential factor, proposed by D'Alembert 1744, and explored by Laplace. The simplest path to understanding quantum mechanics is to understand both the differential and integral-differential classical implementations, and generalize them to involve complex functions. Starting with the integral-differential formulation, the generalization to complex theory is trivial with the aforementioned large exponential factor, now pure imaginary, a phase, again indicating an equal weighting, superposition principle, and thereby directly arriving at the path integral formulation, interpreted as a sum over all paths, where the action of each path contributes its own phase argument.
The path integral formulation to quantum mechanics will be seen to be most fundamental, but not always the easiest to work with. As with the classical theory, the integral-differential formulation gives rise to a differential formulation that is often more useful. For quantum mechanics, this differential theory is often expressed in the non-relativistic formulation of Schrödinger's equation. If expressed in terms of position and momentum interpreted as quantum observables, we find that they obey a non-trivial constraint, the Heisenberg uncertainty relation, and such a formulation is often represented in terms of Heisenberg's matrix mechanics. Note that, given the assumption of an underlying wave theory, we could have presumed an uncertainty principle would exist on that basis alone, as established in the mathematics of wave theory, Benedict's theorem. From that it is required that there be an uncertainty relation on the operators of the quantized theory. Therefore, we could have guessed non-commutation on canonical variables and shown consistency on such solutions, thereby arriving at the canonical commutation relations for operators of the theory merely from it being a wave theory.
An example of where the path integral formulation fails to solve an important task is in solving the hydrogen atom and obtaining the precisely known spectral results that have been observed, as can be done using the Schrödinger, Heisenberg, or other operator approaches. Initial efforts to solve the hydrogen quantization with path integrals failed. The simplest approach to solving the problem is to generalize to a path integral formulation for curved spacetime and making use of analytic time parameter. This will be the first of many examples where analytic time, or a shift to pure imaginary time, will be shown to regularize the problem and arrive at a solution. Understanding time and how it has an analytic aspect is beyond the scope of this text, see end, but hints of such analytic time properties will appear nonetheless, and be noted when they occur.
According to classical mechanics, the atom should be unstable and collapse. There is no collapse, instead there are discrete atomic states, including a ground state, as well as allowed transitions between atomic states giving rise to atomic spectra obeying quantization rules. A brief history of early quantum mechanics theory, such as the Bohr model, is given in section 2.5.2 to follow. These bound state solutions are generally the simplest solutions to the Schrödinger equation, a second-order differential equation, so many easy examples will be given. In a description of atomic matter, as far back as the early quantum mechanics models and their spectral fits, there appears the fit parameter alpha. In the more advanced quantum field theory, Book 5, this fit parameter is retained as a fundamental perturbation expansion parameter on electron-photon systems. Thus, we see the fundamental parameter alpha whenever we examine systems of bound, atomic matter. Likewise, both the Schrödinger and Heisenberg formulations show a new, very small, constant, Planck's constant, the inverse of which provides the large constant for the aforementioned integro-differential formulation. The Planck constant first appears as a quantization fit parameter in an analysis of the black body radiation. The history of the discovery of quantization and of the Planck parameter is given in the next section.
The shift from the real function formulation of reality, classical mechanics, to an inherently complex function formulation in quantum mechanics was a major paradigm shift, requiring reinterpretation of key variables and processes. A new vocabulary had to be invented having to do with quantum observables and classical apparatus. This process began with the mathematical formalisms of quantum mechanics formulated by Heisenberg, 1925, and Schrödinger, 1926. Physical repercussions, such as the Heisenberg uncertainty principle, 1927, began to give a better sense of the new theory, as well as interpretation of the wave function, Born 1927. Even so, there were still major hurdles in the theory due to the observed point like nature matter/charge for the fundamental particles. This requires admission of Dirac delta functions into the formalism, e.g., we need to extend from integration over functions to integration over L2 distributions. A description of early distribution theory-based functional analysis, e.g., as described in Richtmeier, as given by Dirac 1930, is also given.
The relativistic formulation was also done by Dirac, 1934, and will be described in section 6.2 to complete the formal underpinnings of the single-particle quantum theory. Interpretation problems begin to occur in many applications of Dirac's equation, however, and indicates the need for a many-particle theory that is best described in terms of a field theory, and this is the content, e.g. quantum field theory, described in Book 5 of the series. Lastly, we turn to an advanced application involving analysis of a fully generally relativistic dust shell collapse. Upon phase space reduction, this will be what's known as a mini-superspace model, and its quantization can then be directly performed using standard, single-particle, methods already ascertained. This is where the axiomatic quantum mechanics theory of Dirac helps to focus on the need to obtain a physical observable, that is mathematically strictly associated with a self-adjoint operator. Put another way, the parameter domain over which an operator is self-adjoint describes the domain over which a physical observable exists, and a description is possible. So, the dust shell analysis reduces to a self-adjoint Hamiltonian operator analysis that is given in section 8.4. A mini-superspace solution is obtained, but it has key parameters specified by boundary conditions that make the answer, effectively, whatever you put in, with no quantized spectra, thus disappointing in that it seems to resolve nothing vis-a-vis the quantum gravity problem.
However, the tools used in the perturbative and self-adjoint analysis, especially invoking the Kato-Relich theorem, section 8.4, are critical methods in performing the emanator perturbation analysis in Book 7 in the derivation of the constant alpha. The fine structure constant, a shortened derivation, is given in the appendix here as well, and the indications of analytic time and thermality in obtaining the dust shell solution will help to motivate the black hole thermodynamic analysis, done in Books 5 and 6.